My name's Simon. I'm probably, as you can tell from this rather outrageous accent, I'm in the UK at the moment. I'm the author of this book here, what I have written, and some of the content of that book is what's going to be making up a lot of these talk. And also, so what really is the origin of this talk is the pandemic happened, and being an introverted software developer, my social life did not change demonstrably. So I largely spent the whole time in. But my wife thinks that I never get bored. Well, actually, the opposite is the case. I get bored all the time. I get terribly bored terribly easily. And oh, hello, someone's wandering over to me. Ah, thank goodness. Thought he was going to come around here. Right. Um, but what actually happens is I'm very good at finding ways to fill my time. I'm very good at finding projects or stuff to do. One of my friends once said I'm the sort of person, if I get bored and stuck in a room somewhere, I just like randomly learn Finnish or something. And yeah, so this picture here is one of the things I did to fill time during the pandemic. I learned to draw. I'm still working on it. I'm not going to pretend I'm great, but there we go. And the other thing, I've been learning the piano. But also, I decided I'd set myself an interesting project with code to keep myself entertained while the thing was going on. So this is kind of what I'm leading into here. I found a very, 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 very old computer game and converted it into modern functional style C sharp. And what all of that is will require a bit of explanation. So I shall digress for a while before we get on to the project itself. And also, incidentally, there at the bottom of this slide are my contact details. In case anyone ever wants to speak to me again, that QR code there is my Twitter handle. I'm still calling it Twitter because I've heard it annoys Elon Musk, and if it annoys Elon Musk, I shall do it. So it's still Twitter. Okay, come on, come on, come on. There, right. So what is functional programming? In brief, as quickly as I can. It is a paradigm and not a framework. So what's a paradigm? Well, a paradigm is a style of programming. If you want the metaphor of a musical instrument, you can pick a big guitar and you can play many styles of music on the same guitar. You could play rock or pop, or if you have no taste, country and western. But whatever. The same is true of programming. And the C sharp is deliberately designed to support multiple programming paradigms. Uh, in fact, every single version of C sharp since C sharp 3 has contained stuff intended specifically to serve the functional paradigm. And entirely deliberately, several of the guys at the top of the team over there are fans of functional programming. So this is there for us. It is declarative, not imperative. So these are the two of the families of paradigms. There are many families as it happens, but the two big ones are declarative and imperative. Imperative is what OOP belongs to, that is object-oriented programming. And this is more predicated on the idea that you have kind of like figuratively a little robot running around that goes, does this, do this, do this. Oh, a loop. So do. We are directly instructing exactly where to move inside the code, and we tend to start with things like an object which is empty and then build it up and modify it and enhance it as time goes on. That is an imperative approach. Declarative is really quite different. Declarative is the family of paradigms to which functional belongs. And the declarative works more by the idea that you describe what you want at the end, and the actual order of operations is the business of the executing environment and not necessarily interesting to us. It does not have anything that alters the flow of the data and stuff like that. I'll get on to all of that in a minute. So the most well-known form of declarative programming is TSQL, or SQL in its various flavors. Because if you think about SQL, you are starting by describing what you want and then going into a little bit more detail. The select statement is the first thing that you write, but typically one of the last things to be executed. And does this matter? No, it doesn't. It's fine. Thus with functional programming. So the properties of functional programming, immutability, this is that once a variable has been set, it may not ever be changed again, nor any of its properties. Everything is considered to be a const with const properties. Nothing may ever be modified once instantiated. We always start with a line, and then second line is a modified version of the first, and third, and so on. But the first and second lines stay in existence. The metaphor I usually use is that of maths working in a maths exam, where you're writing out your working as you go along, and each line's based on the previous, but the previous lines continue to exist and can be read back. So it has the advantage that if you want to go and check your working or debug, as it were, you can go and see each intermediate step because they still exist. Higher order functions. Scary sounding name, simple idea. This is functions passed around either as the return type from a function or the parameters into a function. So if anyone has ever used link, this is it. You pass parameters into link as parameters, and there you go. That's all that is. Expressions rather than statements. So an expression is something that evaluates to a value, and a statement does not. That's roughly the difference. So statements include things like if, while, for, do, and so on. They change the order of execution but do not evaluate to anything. Functional does not use them. So we use other methods to perform the same functionality, but we don't alter the flow of execution in functional programming. There is one single flow going from the top down to the bottom, and nothing can alter that. Can we entirely achieve that in C#? Ish. I'll get into that. Referential transparency, once again, slightly scary name. It's actually not terribly difficult. Also known as pure functions. So this is the idea that a function may only rely on its parameters and nothing else, and cannot have any side effects. So the infamous example of a side effect would be something like an unhandled exception, an unhandled null exception, or something like that. An exception is a side effect. It causes the flow of execution to change. So we don't generally, that's not a concept that exists in functional programming. The idea that you could pass an object into a function and then modify that object within the function and it affects the outside world, we don't do anything like that either. And frankly, I wouldn't do it in OOP even if I weren't writing functional. Stuff like that, anything that might have a side effect. So it's called referential transparency because the idea is that given the same parameters, you'll always get the same answer back, no matter what happens, no matter what state the system is in or anything. So effectively, you can swap the reference to these two parameters in the function to the value as if they are the same thing. That's where the name comes from. And recursion, are we okay with recursion? Hoping we're all okay with recursion. Gonna be a slightly tough night for you if you're not. Excuse me, just recovering from a cold. Pattern matching, I used to have to explain. This is switch expressions. If everyone's used switch expressions in C#, they pretty much can do pattern matching pretty well these days in C#. This is your switch expression where you can switch on type or switch on the properties of the object and all sorts of things like that. F# can still do a little bit more than C# can do, but C# can do pretty much all of it these days. And it's stateless. So that's not entirely accurate. It does have state, but OOP is typically predicated on the idea that we have a state object which is instantiated, and then we're going to pull bits of data out of it, we're going to push updates into it, and this state object is going to exist for the life of the system and be updated periodically as we go around. Well, we do have state in functional, but state is more like an emergent property of the system. We can't modify a state object. So state objects exist for a moment in time. And if you want to change it, what you do is you have a function which takes the old state object, some instructions and parameter data, and then returns a new state object. So we have a stream of state objects, each one a modified version of the previous one. So state exists, but as an idea that emerges from the system. If anyone has used React.js and used Redux, that's pretty much how state is handled in a properly functional system. So in fact, React.js is also based in the functional paradigm, as is certainly Redux. That is based on something called Elm architecture, which comes from one of the pure functional languages. Are we all okay so far? Yeah. Okay, good stuff. Right. Apologies also for the funky accent. There's not a lot I can do with it. It doesn't wash out, I'm afraid. So if I say anything that doesn't make sense, could be that I'm waffling or could be that I'm just not being very clear. So please feel free to put your hand up and ask me to say it again or more clearly. So why should we do functional programming? Well, there's a few. These are my favorite of the advantages. Reduce code noise. That is, functional code tends to be significantly shorter and more concise than object-oriented alternatives. It tends to be easier to read the intent of the code because there's an awful lot less code noise getting in the way. Things like ifs and whiles and stuff like that. It also tends to encourage good code structure. Things tend to be, code lines tend to be organized by the logical progression of what we're doing, as in first do step one, then do step two, then, and that's actually what tends to happen with the code itself. It tends to mirror what you would describe to, say, your non-technical boss the code did if they asked. It's more testable. Because of this concept of pure functions, we can get close to 100% testability. Close, not quite, certainly not in C#, but pretty close. More robust. Because of the lack of side effects and for various other reasons, we tend to have more code that is much harder to break in production. Oops. Rested my hand on the keyboard there. There is a claim made by purer functional languages that once they are actually compilable and running, then nothing can bring them down. And that might well be true. We can't quite achieve that in C#, but we can get fairly close. So we can certainly massively reduce the amount of possible problems we can get in production. It's more predictable. Again, referring back to the idea of pure functions and things like that. Has better support for concurrency. We don't exactly have a state object, so ideas like resource contention, to an extent, go away. If you're interested in things like serverless or having multiple processes on a queue and stuff like that, or async, then functional tends to support it very well. Now, we cannot fully achieve the functional paradigm in C#. It's just not going to happen. C# supports both predominant paradigms, that is, object-oriented and functional, and it will always support both paradigms. It's roughly at the exact halfway point between the two of them. If you go over to F#, you'll find that that's something like 90% functional with some allowances for OOP, but C# sits in the middle. And for reasons of backwards compatibility, that's unlikely to ever change. And also because of backwards compatibility, there's a load of features that we may or not ever get. A pure functional language has everything immutable by default. That's probably never going to happen in C# because chances are it'd break nearly every code base in the world. Plus, we're always going to have a whole load of objects sitting in the back of the .NET library somewhere, which have never been rewritten with functional in mind, and we're still going to have to interact with them in a purely imperative manner. So, you know, we can get pretty close. We can implement most of this paradigm, but not all of it. So the metaphor that I like to use is that of a shadow. So I've been learning to draw, and I know there's actually about 12 parts of a shadow before anyone shouts out. But broadly speaking, there are two main parts of a shadow. There is the dark, solid piece in the middle, and then the grey, fuzzy bit around the outside. The big bit in the middle, that's the umbra. That is, when I'm writing functional style code, I try and make that the functional area of my system. That is the center of my system. I try and make that as purely functional as I can. And the penumbra, the fuzzy bit around the outside, that's the bit where I have interactions with external systems or with the internals of .NET. The bits where I have to make a compromise to make it work, those bits are allowed to be a little bit imperative. And I try and minimize those bits to the extent that I can push them as far to the fringes of the system as I can, and but try and keep everything in the middle as pure as I can. I think the technical term for this is something like functional core imperative shell for this particular design pattern, but I like my shadow metaphor, so that's what I'm sticking with. So moving on to Oregon, since I mentioned Oregon at the beginning. Now, I had never. Here's my wife, by the way. Say hello, everybody. Yay. She's just off to work. She's not like me, laying about, talking to nice people in Australia. Right. Oregon, yes. So I had never heard of Oregon before. I don't know whether it's a well-known thing over there, but I'd never heard of it. But fine, the Oregon Trail. So the first question, what is Oregon? Well, there it is over there. It's a state in America over on the west coast. Here's some pictures I found of it online, and it looks really pretty. I am not aware of whether there is a conference over in Oregon, but based on these pictures, I'll go. It'll have me. It looks nice. I might have to take my camera. It looks nice. Nike are based there, apparently. There you go. They have to be based somewhere. They're based in Oregon, named after the Greek goddess of victory, in case you were curious. There you go, Nike. The 1980s classic The Goonies is set there. Named, by the way, because they live in an area of their city called the Goondocks, hence Goonies. I had wondered about that title when I was a kid, but there we go. It is set in Oregon. And also the legend of the Oregon Trail, which is what this game is based around. And I shall be getting that in a moment. So as I understand it, there was an incentive put in place to try and encourage folks in settling in America on the East Coast to make their way over to Oregon on the West Coast to get themselves some big, nice bits of farmland and stuff like that to establish themselves somewhere to live. So what started off as a network of trading routes created by fur trappers and the like turned into one long continuous trail that lasted all the way from one side of America over to the other. There it is. You can see that sort of thick black line there. It goes all the way from the Missouri River in the east, all the way over to the other side of America through there's some mountains there at the end, the Blue Mountains. And then finally you reach Oregon, and the folks made their way in those covered wagons that you saw, pulled by oxen. There's also a mountain trail that had to be traversed. This is the best picture I could find of it. You can sort of see it in the distance over there. And hunting as well. So you see the folks there hunting because you couldn't carry enough food for all the months of your journey. Go away, notification. All the months of your journey entirely in your covered wagon, so you had to hunt along the trail for your food as you went. And this game does incidentally have a hunting minigame. It's an entirely text-based game, but it's still, nevertheless, despite being entirely text-based, has a hunting minigame. And I'll leave you to ponder how on earth that's even possible, but it does. There. And also there are forts dotted along the route as well for trading purposes within the game, and these gentlemen on their horses, who I'm sure were treated entirely fairly and nicely, and nothing bad ever happened to any of them or something. I'm not sure, but they'll all be popping up in our game as well. So moving on a step to the 1960s, this is a gentleman called John Kemeny. He was a Hungarian mathematician. Now, I'm not a mathematician, and so don't fully understand everything he was up to, but he had a couple of obsessions. How he became the head of mathematics at Dartmouth University in America, and he was obsessed with the idea of computers as a useful tool for doing maths, and the idea that everybody should have access both to the math stuff and also to the computer. And consequently, on the campus there, they implemented two quite revolutionary ideas. And he did that with this guy, that's Thomas Kurtz. They implemented two ideas. One was time sharing. So back in those days, back in the early days of the 60s, the computer was a gigantic basement-sized thing. And what you did if you wanted to interact with it is that you get yourself a punch card, punch it out in some manner that I don't understand. You would hand over your punch card to the person who administered the computer. They'd tie all of the punch cards up for the day into a batch, hence batch processing. That's where that comes from. And then at some point later in the day, they'd go down to the computer, feed each punch card from the batch into the computer, get the outputs from the computer, which would also be some sort of punch card, I think. And then when you were ready, at some point and a day or so later, you'd turn up, ask for your result from the computer and find out whether your code even worked or not. So that then, if it did, you had to have another round. So, yeah, I can imagine that would be quite a pain. But the time sharing system was the idea that rather than just being one mainframe with one access point, the mainframe would share its time between various terminals dotted around the campus, flicking from terminal to terminal, and giving everyone who used each terminal the idea that they were interacting with the computer in something close to real time, effectively like a multi-user system now, except what the computer was doing was just simply switching its attention constantly from place to place. But it meant that everyone around the whole campus was able to directly interact with the computer, put code into it and whatever, and also share code, because then code could be stored on the computer and called back for anybody to use. They also had this idea of a new programming language. So prior to that, the dominant programming languages were things like Fortran and COBOL. Now, I've never worked in either of those, but I've seen textbooks written and they are really quite hard to understand, at least for me. So they had this idea that they'd make a new programming language, one which was designed to be as user-friendly as possible. So one of the design constraints of the language was that every line should have a verb in it, which would describe the purpose of the line. So here we have a print, that's a verb, and then it prints this string. And then the other thing, for better or worse, it had was the ability to literally jump from line to line. So you had to write a line number on every line to identify it. And then on line 20 there, you could literally go to line 10. So what I've just created is an infinite loop. So not terribly good idea, perhaps, but nevertheless, it's the sort of thing you could do. And it did mean that code in this language was rather hard to debug sometimes. And it was called, incidentally, the Beginner's All-Purpose Symbolic Instruction Code, or BASIC. Visual Basic is an ancestor of BASIC. This is the original non-visual BASIC. They also had an idea for a code word, which at the time was considered quite controversial: input. Now, these days, this does not seem like a big deal, but back then, this was considered quite odd, because computers were considered tools of mathematicians. And the idea that you would break the chain of execution to allow the user to input some text or whatever seemed strange to a lot of people back then. And there were arguments about the inclusion of input in a language. Nevertheless, input stayed. And the very next thing that happened is that everyone on campus started making computer games. There were recreations apparently of things like American football and all sorts of other things, which I dare say were terribly exciting to play in an entirely text-based environment. But this is the sort of terminal that everybody worked on. This is an HP Timeshare terminal. So what you might notice here is there is no screen, because there was no screen. This is in the days before the VDU, before the computer monitor. Effectively, what this is a typewriter tied to a printer with a network cable going in. There's probably more to it than that, but that's the basic idea. So when the code said print, it meant print. It actually printed that text on a printer as a giant roll of paper that you can see there. And so it would just sort of print it. And then if that was a bit of stuff you needed, then you rip it off and take it away with you. There we go. I've never seen one of these in real life. I'd love to, though. So this is the end of the 60s. Moving on to the 70s. These three gentlemen here were student teachers in a university in I think this was in Minnesota. Don Rawitsch, Bill Heinemann, and Paul Dillenberge, and they were teaching a course on the Oregon Trail, a history course. And they had this idea that what they do is make a computer game for their students that would try and instill some of the ideas of what they were teaching a little easier, because you could sit there and play the game, so they created the original 1971 first version of Oregon Trail, a computer game series which still continues to this day. Has anyone actually ever played a version of Oregon Trail, by the way? No? Okie doke. Pascal, you had to start your code with print CRT to tell it to print the screen. Oh, wow. Gosh, Pascal, that takes me back. I haven't done Pascal in a very long time. So, yeah, right. So 1971. And the 1971 version was loaded onto the campus mainframe, and it became a big hit on campus. It was a hugely popular game in its time. Bearing in mind, this is the days before computer graphics, so you had to make do with what you had. And even folks that were outside their circle of students were playing this thing. Now, unfortunately, at the end of the term, the computer was reset, and the original 1971 version is lost to posterity. What they're holding there is a copy that they made some years later. So in 1975, they were approached by a Minnesotan educational company, which is what at least 3 of these letters stand for. And they had the idea that they would take the original 1971 version of Oregon Trail and recreate it in a slightly enhanced, slightly richer form, and they would release it as educational software to university campuses around America, which is indeed what they did. So the 1975 version, the source code for that still exists, and that is what I used as the basis for the project that I undertook. It's not hard to find the 1975 code if you go hunting around for it. This is what the game might look like on a slightly more modern terminal. I do not have an HP Timeshare basic terminal, nor at the mainframe I would require to use it, so I have to make do with a DOS prompt. So, as you see, it's an entirely text-based game. It is 100% text-based. And what you are effectively doing is interacting with a series of menus, which are asking you questions on what do you want to do. So this is the menu system that's setting up the game in the first place. How much do you want to spend on food or clothing or whatever? And then in the game system itself, you are given a set of choices, which are typically marked with an integer value. And then you enter an integer value to say which of these choices you want to do. Do you want to hunt or continue? We'll press 1 or 2 as appropriate. There we go. And like I said, there is indeed a shooting mini game. So still, I will show you how that was done eventually. This is what the turn system roughly looks like in this game. So if we start with our initial purchases, and then we begin the turn cycle, which is a giant loop. Inside the turn cycle, you're presented with between 2 and 3 choices. If you want to hunt, visit a fort to trade for goods, or simply push ahead and try and make more time. Then there are a series of random events which may or may not happen based on various criteria. We may or may not encounter riders on the road ahead. There are various other random events of different sorts. And then if you are within a certain range of mileage, then you may also encounter random events pertinent to mountains. There is finally a check to see whether we have reached Oregon or not based on the mileage you've traveled. If you haven't, we'll go loop back around for another turn. Now, turn here in game time represents something like a week. It's not consistent. There's literally an array of the various dates which it picks from each time you iterate through this. But if we have reached the requisite mileage, then we go for the very, very impressive all singing, all dancing end sequence, which I shall show you later. This is what the original code looks like. Now, I said that in BASIC, it was a constraint of the language that everything had to be a verb. Well, even comments had to be verbs. Rem here is short for remark. This is a code comment. I put these colors in. The original is completely text. I've just put the colors in to try and make this a bit more readable. So this is a couple of rems, that is a couple of comment line comments to describe the code at the beginning. Then dim, which is still in use in does anyone use VB, by the way? I don't know if anyone does, but dim is, yeah, great. My commiserations to you, my friend. Dim is still in use in VB to this day. It's declaring an array. The $sign there, incidentally, is pronounced, for whatever reason, string. So line 30 is dim C string 5, meaning create an array of length 5. And string here is used to denote that it's a string. So BASIC does not differentiate between an array, meaning an array, and a string. They're the same thing, just treated differently, which is not that different to C# in many ways. Then take an input from the player. Now, something I found weirdly hard to get out of the habit of when I'm making this thing is not to refer to the player as a user. I've been in IT for about 20 years, and I am so ingrained in a habit of saying user all the time that when writing a game, I have to remind myself, no, this is a player. They are here to have fun. So take whatever the player entered from the keyboard and input it into C string. If C string is equal to no, then go to line 400. So in C#, we're used to the idea that we go if, and then some sort of predicate. And if the predicate evaluates to true, then go inside the closure that follows and execute this code. Well, BASIC's the other way around. In BASIC, you say if, and then a predicate, and if it's true, don't execute the code that follows, skip over it. So all if logic has to be reversed to turn this into C#, which took an awful lot of scratching my head and staring at to get right. Some bits were harder than others. So this is saying that if the player enters no, so what we're being prompted with is there on line 25, do you need the instructions to how to play the game? And then on line 40, we're saying if they type no, do not type the instructions out. If they type anything else whatsoever, then they get the instructions in full, the poor what's names. And it is quite a lengthy set of instructions. You get the idea of how roughly this works. Thankfully, there was a set of rems right at the end of the code which explains what all the variables mean. Another common feature of basic code is that you tend to get variable names which are often single characters or maybe 2 characters long. I can only guess it was for reasons of reducing the load on the memory. So, because the computers that ran this stuff had a very, very tight amount of RAM available to them. The computer that I grew up, which was a basic machine, had only 48K of memory, and that was an advanced machine in its day at one point. My dad's basic machine, on the other hand, the ZX81, that had 1K of memory, which is probably less than a modern pocket calculator. Right, let's move on to writing some actual game. The first thing I need to do is to deal with the side effects of interacting with the real world. So we in the functional world work on the idea that there are no side effects. We have pure functions with pure results. So there's nothing more impure than a human being. So we need to protect ourselves from any potential strange side effects of the actual human being and an actual keyboard. So on the left here, we have a player, and look how happy they are. See, they are happy because they're playing Oregon Trail, and it's that good a game. And they're interacting with the console, and then if I don't do anything, that will just go straight into the turn engine. Well, I can't allow that. I need to have some levels of abstraction here to prevent strange things from happening inside my code base. So first thing I'll do, since I'm a nice guy, I'll put an interface around the console. And this is just a thin wrapper around it, but it means that for test purposes, I can inject a dummy version of the console to test whatever interactions I want. But that's not enough, because out of the console, actually, it's not just going to be text. 3 possible things can happen. Either the player types something and presses enter, they simply hit enter, which might or might not be a problem depending on where in my code this happens, or an error of some sort could happen. I don't know what sort of errors can come out of console, but it must be possible. And I don't want to have to put a try catch around every single call I make to the console. So what I want to do is encode these three possible states into my code base. And the way I do it is this. So I made a public abstract class called maybe. Maybe is a fairly common functional structure. And it's a maybe of T. So T is a generic, meaning that T can be any type, any primitive or complex class in the whole of C#. And then I inherit off that 3 times. The original is an abstract, meaning you cannot instantiate the base class. You must instantiate one of the child classes. And that can be something to mean they actually entered some text and pressed enter, in which case it has a property called value, which contains it. Now, I've made it generic with a T, but in the Oregon Trails case, it's almost always going to be a string. They could have entered nothing, in which case there are no properties, but it's simply a notification that nothing came out of the interaction with the player. Or finally, an error occurred, in which case the error was caught, and here it is as a property of the error class. It's not an unhandled exception. The exception has been handled and captured deeper within the code base. And here it is presented to you in a friendly manner where it's simply a property that you can examine and pick bits out of if you want. This is a very simple example of something called a discriminated union. I'm not going to go too much into functional theory because that's not really what I'm about. But roughly speaking, it's the idea that I'm kind of approximating it with inheritance here, but real discriminated unions don't use inheritance. It is just a type which is one of these types. So my maybe type consists of one of these 3. TypeScript does this apparently. There is also a code class, a NuGet library in C# called oneOf, which implements this nicely as well. Think of it as Schrödinger's type. If we have the type cat, or cat can actually, when you examine it, be either a live cat or dead cat. And until we open up the envelope of the parent type, we don't know what actual type we have. And so it is with the maybe. And we can actually even pass it around as the maybe all around the system. And for the most part, you may never care whether it's actually a something, a nothing, or an error underneath the surface. It's only when you actually care that you open the envelope up and have a look. So when I write this sort of stuff in an MVC application, I'll typically just pass maybe to maybe to maybe all around the internals of my system. And the only time that I collapse the maybe down to a concrete value is in the controller action, where it actually matters to the end user what actually happened from the internals of the system, whether it worked, failed, or the record that we were looking for didn't exist, whatever. So that's this one. Here's a read line based around this concept. So we've got a try catch around it. So if an exception occurs when going to the console, then we return a new error type, and the exception that occurred will be captured inside the error. If you want to do logging, now is a good time. And otherwise, the read from the console, look at that result, examine it to see whether it's null or white space. If it's null or white space, return nothing to say that the user entered nothing. Player, see, it's not easy. And if it's not null or white space, then return a new something and have the something inside it, which is a string, again, in our case. There, and this is how you'd actually consume it, maybe out in the controller action. If this weren't a console app, which it is, we'd use a switch expression. And the switch expression can switch based, you can pass it the parent type and then switch based on which child type is the real type of the object. If it was something, nothing, or error, and you can even put in a local variable. So on the something line, if that something is the correct case, then the S there is a local variable which contains the the parent object recased in, re-switched into a something now, so that we can access the properties of it. So this is nice and elegant. In this case, I am taking the possible 3-state maybe and collapsing it down to a string. which then I could pass to the player, user, or whatever. This is just an example. Also, I need something that represents operations which have no return type, because not everything actually returns a value, but I still need to be notified as to whether it worked or whether an error occurred. So I've called that operation. I've also seen this called result and other things. So in my case, I'm making an abstract class operation. So this is another discriminated union. And then this can be either success or failure. Success is empty because there's no return type, but it simply indicates by being a success that it worked. And then if it didn't work, then we return a failure, which has the error which occurred captured inside it for you to examine or use as you need. Oops, come on, there we go. I created an extension method too. Now, extension methods get a bad rep, but I quite like extension methods. They have their uses. Just don't put business logic in them. Once you put business logic in an extension method, then you're basically hiding important stuff, and you shouldn't do that. But try operation attaches to T, and T being a generic means it attaches to everything in the whole of C#, and it takes an action, which is whatever code you want to pass into this. So what this means is that I can attach to any object I like in the whole of C#, and then allow you to pass me a load of code that interacts with that object, and whatever it is, I will take that object, pass it into the action. If it doesn't error, I'll return a success. If it errors, I'll return a failure. And this is my version of a write line to a console. So message, that is the string, which is a params with a string array. So you don't need to, you can have multiple lines if you want and stuff like that. .try operation. Now, I've had to use a for each here. I did say compromises were necessary in C#. I'm not aware of a way to write multiple strings to the console as an array, so I'm doing it in a for each. It's a compromise, but there you go. You have to make them. But since we are interacting with the console, we're effectively out on the fringes of the system, so I don't really have too much of an issue having the occasional for each like this in us, so long as we don't allow this to happen deeper into our code base where I expect it to be more purely functional. Now, I actually went a step further and created another level of abstraction sitting in front of the first. So we've got our raw output from the console, which is something, nothing, or error, but logically within the game, something subdivides into two possible states. The player could have entered text or could have entered an integer. In Oregon Trail, that is very significant because actually about 95% of the time, we need the player to enter an integer, and the integer is important. Other times, we've just got a notification of 5 minutes left for the meeting. Are we not going to get kicked out, are we? So I may need to know this. So by having these four states now, I've baked the idea of the integer input into the system. And come on. There. Here's my modified version. So I've now got another discriminated union, user input, and user input consists of empty input, meaning they just pressed enter. Text input, they type some text of some description, and here's the text as a string. They entered an integer, in which case here is the integer already parsed into an integer for you, because otherwise I would literally have to call int.tryparse all over the system. But by capturing it at this point of sort of purifying the input from console into the internals, it's already an integer. So there's actually only one int.tryparse in the whole of my system, and it's used everywhere. But it means that inside the system, inside the functional core of the system, I already know if something was an integer and it's already wrapped to the correct type. And also the exception. Once again, if an exception occurred, I've got it captured. There. And here is a get input. So I want a prompt to write something to the player. So do a console.writeLine, and then I get back a write result, which is an operation. That's a success or a failure. Switch on the write result. If it was a failure, then return an error of string out to the player to tell them this attempt to write to the console failed. Otherwise, do a read line. Then take the result of the read and then do a switch. Check if it was a something, that is, some actual content occurred, and do a try parse to say, was it an integer? If it was an integer, we're going to return an integer input and parse the string into an int. Otherwise, if there was content, then we'll check against null or white space. And if it wasn't null or white space, then text input. If it was an error, then return an error. And if there's anything else which means that it was a something, but it was empty, then we'll return an empty input. There. That's the final form of my interactions with the player. And this is an example of how I do the do you need instructions code. So do I've wrapped all of this into a class that I call user interaction. Should have called it player interaction. I did say this was hard stuff to do. So get input, do you need instructions? So then do a switch, which says if it was a text input and the contents of that text move to upper just to make sure the case that are not case sensitive equals yes, then collapse this to a Boolean true. Any other case will collapse to a Boolean false. So if they entered an integer or just hit enter or an error occurred, then we will consider that a false. And there's a version of writing the rest of that. Now, I've got an if here. Now, this is only a single line if. I don't have any braces, so I'm not too fussed about this if. But that is checking to see whether the Boolean that the previous line evaluated to was a true, in which case write out the message. But this is my code, so I want to try and see just how functional we can make all this. So I wrote a method called write message conditional, which takes a Boolean condition and a string. So, and then based on the condition, it decides whether to write the message or simply ignore it. Which means I could just write a single flow without having to write an if statement. It's kind of handy. So here's the complete set of code. First, write out to the user to say, do you want instructions? Take whatever happened back from the player and collapse it into a Boolean, either true to say yes, write the instructions, or false to say don't. Then write message conditional, pass it the contents of display instructions, which is a true or a false. And then based on that, the code inside write message conditional will know whether to write the rest of the message or simply not to. Right, moving on to the next phase, which is to manage our inventory. That's the first stage of the game, is to set up our spends. We start off with $700, presumably dollars. It doesn't actually say what the currency is, but presumably dollars. And our inventory consists of oxen, food, ammunition, clothing, and rather ominously, miscellaneous supplies. Now, I did wonder for quite some time what on earth miscellaneous supplies might be. Turns out, if you examine the way the game works, it's medical supplies. I don't know why they called it this, but I tried as best I could to replicate the nomenclature used in the original code. To an extent, I did not use things like a string as variable names, but I tried to reflect the logic that they used. And internally, they call it miscellaneous supplies, and so did I. There is probably a version of this that will come out one day where I'm just going to feel free to do whatever I like with it. And maybe I'll change everything then, but no. Here's the original code and what it looked like for setting up our inventory. We're setting a whole load of variables there, K8, S4, F1, and F2, and so on to 0. Writing how much do you want to spend on oxen? Take an input and store it in A. If A is greater than or equal to 200, then skip to line 900. Now, if you look at the lines before line 100, between 870 and 900, it's an error message. So what they're saying is, if they've spent more than 200, then that's good. Don't write the error message. If they spent less than 200, that's not good. Write not enough, and then skip back to have another go. Same on line 900 there. If they spent less than 300, that's good. Otherwise, write you spent too much and have another go. And then move on to food. So what that means is that the requirements for oxen spend are the player must spend between 200 and 300. Anything else is considered invalid and they have to have another go. With all other inventory items, the requirement is simply non-zero. The first version of Oregon Trail from 1971 had a bug, incidentally. It allowed negative values to be spent. So you could spend negative amounts of money on food and suddenly make yourself randomly a millionaire by pulling money out of nowhere. And this is what the chain looks like. So we start with our oxen, check to see whether it's within the right bounds, then move to food, check it's not zero, ammo, check it's not zero, clothes, not zero, miscellaneous, not zero. Check that the entire spend is not less than, is not more than 700. If it's less than 700, we're okay, proceed with the game. If it's less than 700, then we have to loop back around again and start the whole process again. So, recreating this in code, let's see how functional we can make this. This is a not terribly functional way of doing it. So first off, call get input, say how much do you want to spend on your oxen team, and then do an infinite loop while true. The idea being that once I reach the conditions that I want, I can exit out of this loop. And we'll get take that input, check it's an integer between 200 and 300. If it is, then return that integer. If it's anything else, then write the error message and then carry on looping again and again and again and again. Now, this is what I refer to as an indefinite loop. So can C# do indefinite loops safely? Well, there are ways. So this is method one. This is recursion. This is a form of tail recursion. That is, this is a purely functional bit of code. And what it's saying is, once again, do I check? Take the user input. Is it an integer? Is it an integer between 200 and 300? If it is, return that integer. Otherwise, call the function again. Call the function again to say, try again. Now, this will accurately create an indefinite loop. But C# doesn't handle recursion all that well. What we're doing is adding to the stack every single time that we call recursively the same function again and again and again. Now, if you're sure that it's only going to take a few iterations, it's probably not too dangerous. But as I know from having done the advent of code in the past, if you try and use recursion where there are thousands of lines of iteration, you're going to explode the stack pretty quick. F# actually has a feature called tail optimized recursion calls, which means that if you do recursion in F#, it's safe. It will not explode the stack via the magic of, well, actually, if you look under the surface, it turns it into a while loop. But nevertheless, inside F#, you are writing recursion and it's safe to do so. C#, on the other hand, it is not. Now, I have looked into it, and you can, if you want, put a post-compile action on this to flick a code switch in the intermediate language to turn on tail optimized recursion calls in your code, but I don't recommend doing that. Sounds like a recipe for something that could break your code base without ever really being clear why. So I created an extension method called iterate until. So what that means is give it 2 blocks of code as func delegates. The first is, here is the loop, basically the body of the loop. Generate an object at the end, which can be examined. And the second is a func which says, take that object and convert it to a Boolean. That is, do a check to see whether the loop has completed or not. So towards the bottom there, you'll see my loop end condition. It's that x should be an integer between 200 and 300. And the lines of code before that are the body of my loop. That is, go and get something from the user and prompt them if it's wrong. And iterate until will carry on doing this process again and again and again and again until such time as we get a Boolean which is true. That is, the conditions that we want to end the loop are met. And we can return the whole thing. So what is the magic behind iterate until that makes this possible? It's a hidden while loop. It's really all it is. This is fundamentally the only way to do it. Even in F#, your recursive calls are still hidden while loops. So there is no other way. The technical term for this is trampolining. So it's sort of like trampolining a function call and get out. But really, hidden while loop is what it all boils down to. A question: can I expand on how F# functional is able to make recursion safe and not explode the stack? Right. I'll kind of show you in just a second. So this is actually a feature which is available in intermediate language, and like I say, it's available to C#, but by default in C# it's switched off. So you've got to mess with the low levels of the compile system to make it work. In F# it's on. And what it means is you effectively just write the same recursion in F# and it just doesn't explode the stack. But what it's doing, because of course the thing with .NET is that the code you write is not the code that executes. It takes that code you write, converts it into intermediate language, and then the intermediate language is what is actually executed. So in the intermediate language, it uses a goto statement. So goto, like in BASIC, still exists. And what it does is simply have a check to see, is the condition met to terminate the loop, in which case, if it's not, go to the beginning. Go to the beginning and so on until the condition is met, and then it passes the go to. It's effectively a hidden while loop, which is, as far as I'm aware, fundamentally the only safe way to do indefinite iterations. You can do go-tos, incidentally, in C#, in case you were curious. There it is. That's a go-to. Loop beginning is a tag, which I have created. And then a couple of lines later, if my condition's not, actually, that should have a not in it, then I go to loop beginning. So I've done away with the for loop, but effectively I'm implementing the same concept. And this is roughly what your F# code would probably end up looking like in intermediate language. But in F# you just write tail recursion and it seems fine. So moving on from my oxen spend, I could go on to the get non-zero spend. Now they're all the same. All the other items are the same. So I'm just giving item name and just saying, based on item name, how much do you want to spend on item name? Iterate until they enter an integer and it is greater than 0. Other cases result in an error message being displayed, and then iterate until finally we get the condition we want, which is an integer greater than 0, and then return the integer. Incidentally, the green underline there is complaining of possible null exceptions, because according to the compiler, it can't guarantee that final input is an integer input, which is interesting because fundamentally I can guarantee that that is true, because I won't allow this loop to terminate until that's true. So the compiler is obviously unable to realize what I've done. Silly, silly compiler. And this is the system I used to just loop through them all. I used an enum and a loop and just basically called this function again and again. And each time it looks at what was the last inventory item you've got in your list, in which case make the next one and use an enum to mark which inventory item this is and with the non-zero spend on the other side, and just loop through them until we have an inventory item array with the correct number of inventory items, which is 5, I think. And that's my whole process for getting the initial inventory. Start with an empty inventory, iterate until I have 5 items in it, and then once I've got 5 items in my inventory, check the complete spend. If it's greater than 700, then now I actually am calling the original function again here. I'm actually making a recursion call here. But my reasoning is that I'm pretty certain that there's only so many times that my player is going to go through that entire menu system of entering inputs until they're just going to flip the desk in frustration because they clearly can't get all the spends right. So I feel safe here using recursion. And if we didn't recurse back to have another go, then we can just return all of our spends in inventory. It's a record as it happens, an inventory class, whatever. There. Now this is the main engine that runs the game. There's an interesting bit of hidden logic here. So I made an extension method which attaches to game state objects. Now the game state actually is a record type, because record types were the feature that was added in for functional programmers. It's an easy way of replicating an old object with a modification. Continue game attaches to all game state objects, and it has a bit of logic built into it that checks to see, has the game ended yet? That is, has either the player reached Oregon or died along the way? And if any of these ever evaluate to say that the game has ended, then the function call which is passed into continue game will not be executed. So let's say, for example, we're running a turn. We'll do the start turn sequence, take an action, we'll eat. There's some mileage updates that have to be done there, and then riders on the trail. Now, let's say that the riders turn nasty and the encounter turned fatal, so we are now dead. Then passing into the next continue game, handle random events, that continue game will check to see, is the player dead? Yes, they are dead. Therefore, do not trigger handle random events. Then the next one, the mountain crossing, that will check to see, is the player dead? Therefore, do not run the cross mountains functionality. It means I can write one flow of events in a nice, easy to read manner like this, but I don't need to bother with if statements all over the place that say, check to see whether the game ended, in which case don't do this. I don't have to do any of that. It's all baked in. Now, this is an incredibly simple version of something called a monad. I'm not going to go into monads any further than this, and technically they're not because there's a few rules involved, but in principle, this is roughly what a monad does. I'm not going further into the M word here. You can read my book if you're really interested. And then the final condition for my iterate until is that the game is over. Now, given that then that this iterate until will carry on blasting around again and again and again and again and again until the game is over. Therefore, once the game is over, we go to the end game sequence, which is very, very impressive indeed, as you'll see in a bit. This is what continue game looks like. It's a check against game state and takes a func that turns old game state into new game state. And it's a check to see, is the game over or is the player dead? Now, apparently there is a cliche with Oregon Trail with the later versions that everyone ends up dying of dysentery. Well, in the 1975 version, you cannot die of dysentery. You can die of pneumonia or injuries. Those are the only two things. Cheery. But what this code does is check the two conditions, game over or dead. If either of those are true, simply return the original game state unmodified. Otherwise, run the function that converts the old state into the new state. If you want to see a very good article describing this concept, there is one written by Scott Velashin called Railway-Oriented Architecture. I recommend it. It's based on the idea that each of these continue games is like points on a railway. And at the top here is the game is continuing, and at the bottom the game is over or the player is dead. And each set of points is a check to see should we switch. But we start up here in the top path to say the game is still on. So should we continue? Should we continue? Should we continue? And so on. And if at any point the game is over for one reason or another, we switch to the other path. At which point no further functions are executed, and we just glide to the end of the chain. It's nice and elegant and surprisingly powerful when it comes to writing compact code. So moving on to the other parts of the game, I drew all these pictures, by the way. I spent a year or so of pandemic learning to draw, so there's no way I'm not including a few drawings in here. So I did say that there was a shooting mini game. So here is how I shall show you how in 1975, with no computer screen, you were able to write a shooting mini game. Here it is in all its glory. So you tell the player, type bang. Take basically the next few lines are taking the input from the player and the time it took for them to type. And if they typed bang, then the output is the number of seconds it took for you to type bang. Otherwise, you get back 7. There's always an upper limit of 7 inside this system. So if you typed BANG correctly in less than 7 seconds, then your accuracy is however many seconds it took for you to type it. I seem to be able to type it sub-second on my keyboard. Now, I don't know if that's just an artifact of the way that C# works compared to BASIC, or if I'm just very fast at typing. But if you are inaccurate, or you take more than 7 seconds, then we just round down to 7. There you go, a text-based mini game for shooting. Here's my replica. I called it gunshot client. So I'm injecting a time service, which is actually a wrapper for datetime.now. I can't use a datetime.now in my code because my code line should have no side effects. And datetime.now is literally different every time you call it. So I can't use it. I have to inject a time service, which means that I can inject in whatever time I happen to want to use. Call get current time to say start time, do an input to say type bang, get back the result, and the result is equal to it was a text input and the contents of the text input were bang. That will evaluate to true, anything else will evaluate to false. And time taken is equal to, was it a hit, in which case if it wasn't a hit then it's a 7. If it was a hit then we'll compare the current time to the start time, and that's your accuracy. And then finally check to see whether you were greater than 7. If you were greater than 7, round to 7. Otherwise, whatever time, 1, 2, or 3 seconds is your result. Here's my version. Does anyone remember these guys? I bet you all flipping remember the little ponies. Who remembers the big guy with a gun? Wasn't he awesome? Anyone remember Brave Star? Did it play in Australia? I don't know. But it was a cartoon series in the 80s. I used to like it. But this section is Riders on the Trail Ahead. So this is one of the sets of random events that can happen. And one of them is that you encounter riders. Now, you would not believe it, but this little block of code here is the bit that I spend the absolute majority of the time staring at, trying to work out how I could convert it. Because all Boolean logic effectively in BASIC is the reverse of what you would expect it to be in C#. Because in BASIC, like I said earlier, it is if condition is met, then skip. And I had to reverse it all to if condition is met, don't skip. And with riders, there is 3 levels of random check that has to be done to finally get yourself to an answer as to what's happening and what the player can do. And it took me a long time to work out exactly how to abstract it out into a way that made any sense. But the oh, excuse me. What it boils down to is, should the player encounter riders, and that is based on a large polynomial equation there, based on m, which is mileage. So the chances of encountering riders are different based on which part of the route you're on. Given that you have riders, do they look friendly or not, which is a 0.8 probability roll there. RND is the same as it is in modern languages. It's a random integer, well, it's the random decimal between 0 and 1, which you have to multiply up if you want it to be anything other than between 0 and 1. So you would then check to see whether they do or don't look hostile. Then the player makes their choice of what they want to do. And then finally, we make a choice to see, okay, were they actually hostile or not? And that will affect the how many bullets we used, whether we have to do some shooting, how many miles the player covered, whether we lost food or miscellaneous supplies, that sort of thing. And there's my check first to see, should we encounter them? So that disappearing off the screen there is just a replica of that equation. And I'm going to do a random, I injected an RND, that is another thing that I can't use. A random number generator, of course, is also not pure. So I have to inject an interface. RND dot between 0 and 10, check the equation. And if it's less than 10, then there are riders, in which case run the riders and update old state into new state. Otherwise, pass unmodified state back. And there's the rest of it. Do a check. Do the riders look friendly, which is a probability roll? Are they what they seem? This was my replica of what was actually several nested if statements in the original. And then riders are actually friendly is equal to riders are not what they seem, and the inverse of look friendly, or they do look friendly. There. That doesn't take very many lines of code here, but my God, it took me a long time to try and work out what the code was doing and exactly how to work this out logically. So write out the message based on whether they looked friendly or not. Ask the player for some instructions. What do you want to do? Run, attack, continue, or circle wagons. The attack might include a quick round of shooting minigame. Get a value back off them, which must be an integer between 0 and 4. And then given that, do a switch statement which says were they based on were the riders friendly and what was the player's choice, in which case we can update the old state with a new mileage, or in more advanced cases run to shooting mini games or whatever else needs to happen. Anything else just results in old state being returned. And then that's how you end this in the end. And this is one of the many ways in which you could end up dead. So if you encountered the riders and you used up ammunition, and your ammunition is now less than 0, you are now dead because you ran out of bullets. So there you go. That's one of the ways. So moving on to the final part of the game, this is the all singing, all dancing, no expenses spared end sequence of the game. So this is a check to see whether you've reached the correct number of mileage. And then finally, we have the message written out there in between lines 4012 and 4020. Now, do you notice the sort of weird 7 speech mark characters scattered around the text there? This was a special character, which was a signal to the terminal to ring a little bell, because there was a little bell attached to the terminal. So how this would work is you would type out as a new ding, finally arrived dinged at our ding gun city ding, like that. I have heard it suggested that this might play a tune or something with the way it's spaced. I don't know. I don't have the machinery to check. If anyone ever comes across one, let me know. I suspect it's just basically going ding, 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 like this to celebrate your amazing victory at making it all the way to the end of the game. Incidentally, the game is not actually very hard to beat. I've played it quite a few times testing this, and I can beat it fairly easily. So other things I've got in mind to run into and try and do the same process to. This is another game from 1975. This is the very first Star Trek game ever made. It's called Super Star Trek, and it's actually surprisingly complex. It involves you flying around the various areas of the universe, finding Klingons and killing them all. And you win the game by killing all the Klingons, which to me seems definitely entirely in the spirit of Star Trek. But there you go. The E with the 2 little chevrons either side is the Enterprise. And I think those stars, those asterisks are stars, and the Klingons are there about somewhere. And you type in 3-letter commands to tell it what you want to do, whether you want to fly around 5 phases or whatever. So I've actually already started this one, and it'll probably take me a lot longer because the code is technically shorter than Oregon Trail, but it is incredibly dense. There are multiple levels of arrays all over the place because it has things like capture the original state of the system, the modified state, so we can do resets. Plus, there's various sectors of the galaxy, and each sector is contained its own element of an array. So it's quite complex. I'll get there eventually though. This is the sort of thing I do for fun. Now, I am a massive fan of Doctor Who, and this is one of the very first Doctor Who computer games that was written in the early 80s, and I definitely want to have a go at doing this one. No picture of the Doctor on the front, incidentally, because they were in the process of shifting from Peter Davis and the 5th Doctor to Colin Baker the 6th, so they weren't sure which face to put on the cover, so they just put a rather nice picture of the TARDIS instead. And this game is colossal. It's written on a BBC Micro, and the game is so big that the data for the game is actually held in compressed form. And the first thing the game does is uncompress a page of memory and start running it. And then when you move to the next bit of the game, throw that away and decompress another area of memory. So it's going to take me a very long time to decode exactly how this works, but it's a huge game and probably worth playing. Zork, because this is one of the granddaddies of the text adventure game, and this one's pretty epic. I'd definitely love to have a go at messing around with Zork, but this one is pretty colossal and written in its own custom language. So this again, it's a thing for the future. So finally, once again, if anyone is interested in anything I've raised here, I have written a book on the subject, Functional Programming with C#. This URL, feel free to use it. O'Reilly have provided it for me. It gives you a month free on their platform, so feel free to scan this and get yourself a month free. I'd be awfully grateful if you would read my book. I've spent a long time writing it, nearly 2 years. It is a very, very silly book. Here it is again. Technically, I now own the largest quantity of tech books I've ever owned in my life, and they're all the one I wrote. There's about 3 boxes of them down the corridor over there of author's copies. If we were in person, I'd hand one out, but sorry. Apparently the expenses of your meetup did not extend to flying me all the way to Australia. Oh well, maybe next time. But there you go. I've tried to write it in such a way that I've taken the gentle slope approach. It starts with C# that will seem completely familiar, and then each chapter just slightly builds on the previous and hopefully never overwhelms you, because I know what some of the formal definitions of things like monads and all the rest could look like. They can look terrifying. I've tried never to be like that, and always to be quite gentle with the reader. It's also very silly because I don't write books any other way. There are many references to Doctor Who concealed within it as well. Okay, that is my talk done. Does anybody have any questions at this point? Going once.
Anyone in the room?
Yeah. Oh,
yep.
I have a question. We have a question.
Let me bring a microphone over.
Thank you kindly.
That is the microphone.
Yeah, I was just wondering if you if you ran your game and the original game at the same time with the same input, or do they do the same? Like, have you like made it identical?
It is as it should be. I tried to model my code as exactly on the original, with obviously the caveat that I'm turning it into functional. But yeah, it should. I've never actually tried that exact experiment of side by side, but because of the random number generations all over the place, I'd never get the exact same result back anyway. But it should. That is the intention. It should. Oh, and although the number of lines of code, incidentally, I counted it up. It's about 1/3 the size of the original. Isn't functional programming awesome?
Well, because the way you did the random number generator, if you use the same algorithm, you just supply the random service.
Yeah, I could, but the problem is with the original, I can't know which random number it got because it's all hidden inside the basic execution environment. I can't know which random number it was. If I could, you'd right. I could actually literally replicate everything, but as far as I can tell, I've played both versions, and as far as I can tell, they feel about the same. One of the only things I can't do is the ding, 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 ding. I can't do that. And in fact, the original work.
That's one of the ASCII characters, isn't it? Like Bell or something?
Ooh.
Yeah.
I'm just wondering if you can.
Okay, maybe I can do the ding. One of the other differences, which my code doesn't currently do, is that the original code wrote a letter at a time. I write a line at a time. It writes a letter at a time. So yeah, if I switch around, I'd probably have to switch my write statement out so that it became a for loop going through the letters one at a time. And then if it comes across the ding, then it runs that ding, like you say. Although to be honest, the sound is muted on my computer 90% of the time, so I'd probably never notice the difference. But yeah, I probably could then. I probably could, but I have to rewrite the write to be, like you say, a letter at a time and know about the ding. But
Thank
you. No worries. Other than that, though, as far as I can tell, they are the same. Oh, another question.
Have you tried using the C# language extensions library?
Oh, LanguageX. Yes, I have. I have another talk called Functional Programming with C#, and I do briefly cover LanguageX. LanguageX is very good. They're a lot more purely functional than I am. I'm not entirely pure to the paradigm. I am a slightly pragmatic functional programmer. LanguageX is very nice, and I have used it a bit, and I like it, and it's worth a go. I personally prefer to write my own, just because the amount of code you need to write is hardly anything really, and it means that you're sure that you're getting a good understanding of what you're doing, and you're sure that it's also going to work the way you want. So my maybe is 3-state, whereas a true maybe is actually only 2-state, something and nothing. I like my 3-state one because error is also a state, at least in the C# world. In a purely functional environment, there's no concept of an unhandled exception, so you don't need to worry about that. But in the C# world, we do. So there's one reason I don't use LanguageX, but there's nothing wrong with LanguageX. It's very good. There are a few other functional libraries around. There's literally a section in the back of my book here about the various libraries I tried out to give comparisons to. So one of is very nice. Yeah, C# functional extensions, that one. There's a couple of others that I liked as well. There's functional.maybe, which is another implementation of the maybe. So there are a few out there. They're all good. They're all fine. I didn't find any I didn't like. If you want to use them, I would have no issue with it in your code base, but I like to roll my own. It's just what I like to do. I hope that answers your question.
Any other questions? Yeah.
I am already married, by the way. Sorry.
I noticed that you're using states. Does that make it hard to test functional software? Because are you able to create a state as a starting point to then test a function? Or do you have to go and play the game right from the start to get to a point to then test that, if you're looking at sort of unit testing?
No, yeah, I understand what you're asking. Yep, no, it's actually quite easy because nearly every function which modifies state takes the old state as a parameter. So what you do is create the previous state in your test, the previous state. You imagine what the previous state would have been, pass the old state in with the instructions, and then get back the new state and then assert against the new state. So no, in automated tests, I just do I know exactly which bit of functionality I want to test, create the state necessary for that. In the case of things like riders, then I'm preloading the random number generator so that I guarantee riders are going to happen, and then see what happens when I get the state back. I also mock the user interaction, the player interaction, so that I make the choices on behalf of the player via my mocks. And in fact, in the case of, I tend to use the mock library, and you can do things like have mocks which have a couple of different responses based on which call in the sequence this is. So if I'm expecting 3 calls to the user to be made, then you can literally tell it that, do return 1, then return 3, then return 2, or something like that, so that I can simulate the player sitting there and making their choices to force, say, riders have occurred and they don't look friendly, and the player chooses to fight them, and so on. So I can simulate all of that, but only I only have to simulate that exact turn. I don't have to simulate the entire game to that point. It's fine. So I would say testing with functional program. No worries. I would say, generally speaking, testing as an automated testing with functional programming is easier compared to the object-oriented alternative. So
it's not necessarily related to functional, but since you're able to create those states, are you able to just map over those and see what the probability of winning is for any given input?
Ooh, we're talking statistics now. You probably could. So I have another talk which I do, which is about generating your own book by Jane Austen using Markov chains. I don't know whether familiar, but basically is that Markov chains are a way of capturing probabilistic systems and the state transitions between them. So you could, but that's way outside the scope of this. But I would use have a look at one of my Jane Austen talk, and you'll see what I mean about Markov chains, and you could use those to make yourself a probability of winning. I also use them to do things like model Monopoly boards and work out what's the probability of being on any given square of the Monopoly board and stuff like that. So yeah, you could. I've never actually done that, but yeah, it'd be something. But then there's also the player choices, which are not probabilistic. So I suppose that's a tricky one. It's an interesting question, and I'm going to go away and ponder that. I suspect, based on personal experience, that your chances of winning the game are pretty high. Because I won most times, and mostly I won by just pushing on all the time, just like forget all of your problems and just keep pushing on. That tend to be the way I found to win easily. So sorry, not a very complete answer, but an interesting question, and I shall go away and think on it for some time. Any further questions?
I think we're all good. I mean, will you thank Simon for presenting to us tonight?
Thank you, everybody. It's been lovely.